Hello and welcome to this video. In this episode, I will show you all the equations that I created that describe the reflection of light off a one-dimensional surface in two-dimensional space. And we're going to use this set of equations to figure out the solution to the more specific problem that you may have seen in the thumbnail for this video. So the problem that we are trying to solve today is given a satellite in the shape of a parabola. Where should we place the receiver to maximize the signal that we receive? So where should we place the receiver such that at y is equal to 5, it bounces off at this point and travels somewhere over here. This point will bounce off at this point and travel somewhere over here. So where should we place the receiver in order to catch that signal? Well, I'll show you. First, let's derive a general set of equations that describe reflection of light off a 1D surface in two-dimensional space. So I'll explain this diagram over here in a little bit, but that's what we're going to use to model the problem. So before we get started, I'm going to explain a prerequisite concept. So this concept is about retrieving from vectors A and B the vertical components of A, the unit vector orthogonal to the projection of A onto B in the direction of the vertical components of A, which is over here. So this is the vertical components of A, and we're going to get that by saying, well, we have A over here, and we're going to subtract the vector projection of A onto B, which is over here. That's where its head is. So you have a vector over here, you have a vector over here. We subtract this one from this one to get a vector over here. And then we're going to normalize it by the magnitude so that we get a unit vector v hat. So now we're going to discuss a second prerequisite concept. And what this is about is the calculation of a unit vector in the direction of A projected onto B. So the tail is going to be over here, and the head of this vector will be over here. So that is A dot B over the magnitude of B multiplied by B, which is, it's going to be this vector over here. His tail is going to be over here, and his head is over here. But the problem is that when we divide by the magnitude of this vector, the vector is always going to be in the direction of B. But we want it to be in the direction of the horizontal components of A, this over here. So in order to maintain that directionality, we're going to divide by the magnitude, or sorry, not the magnitude, but the absolute value, since it's a scalar, of A dot B over magnitude of B. And that's going to give you a positive or a negative sign. If it's a positive sign, it's going to be in the direction of B. If it's a negative sign, it's going to be the opposite of that, the opposite of the direction of B. And whether it's positive or negative depends on the direction of A, which is what we want. So that's going to be a positive or negative sign. And when you divide by the magnitude of B, it's going to give you a unit vector. So that's exactly what we want. So we can simplify it to this expression over here. So I know that this may seem a bit overwhelming, this entire giant set of equations, but I'm going to break it down into smaller pieces. So R of t is the path of a single light ray prior to hitting the surface, and the surface is described by S of u, which is this squiggly line over here. X hat S, which is over here, and over here in the diagram, that is the unit vector in the direction of dr by dt, which is over here, projected onto the surface at that point of intersection. R hat rev, that is the unit vector in the reverse direction of dr by dt, which, and we'll see why that's important later. So y hat s, that is the unit vector in the direction of y hat s is over here, and over here as an equation, over here in the diagram. Y hat s is the unit vector in the direction of and the direction of r hat rev, the vertical component of r hat rev, that is orthogonal to x hat s. So these two vectors are orthogonal. So additionally, r hat refl, or reflection, that is the light ray path after it has been reflected from the surface. And these thetas are the incidence and reflection angles, which are equal to one another, because that's how light rays are modeled when reflecting off a surface. It must be so that their angle of incidence and reflection are the same. All right, so now in terms of the equations, we model the light ray prior to hitting the surface as a straight line parametrized by time t. Or it should actually be path p, because it's a path. But as you'll see, it still works. We're going to parametrize by time. So, and the slope is going to be m. M is the slope of the line. X hat s is calculated by doing what we did in prerequisite concept 2. We find the unit vector in the direction of the projection of dr by dt projected onto ds by du at u naught, because u naught is the point of intersection, or sorry, the u at which s of u and r of t intersect. So the formula for y hat s, it comes from the application of prerequisite concepts 1. We find the unit vector orthogonal to x hat s in the direction of the vertical components of r hat rev, reverse, where r hat rev is just -1 times dr by dt over here, and normalized by the magnitude to get the unit vector. Then what else do we have? We have so in terms of solving for theta, we know that the dot product of x hat s and wait, where is it in my equations? Oh, yeah, it's over here. We know that the dot product of x hat s and dr by dt, where dr by dt is equal to x hat plus m y hat, dr by dt is equal to x hat plus m y hat, is the magnitude of x hat s times the magnitude of dr by dt multiplied by cosine of theta, hence the equation over here when we rearrange it. So we can see this more clearly, this equation over here, if we kind of extend this over here, we get like a theta over here, the same theta, if we were to extend r rev, and that's what we're using to like find this equation over here. So finally, in terms of our refl, we have that's parametrized by t, or time, and it is going to be equal to this expression over here, where the slope is actually the tangent of theta, and the line is going to start at s of u naught. It's going to start at the point of intersection and go on to whatever points are next. And oh yeah, one more thing. R refl xs0, that is going to be equal to 0, and so is R refl xys0, because those are the starting points in the in the s coordinate system. You know, x hat s and y hat s, they comprise the basis for the S coordinate system that starts at S of u naught. So our line is going to start at 0, 0 in that coordinate system. I know that took a while to explain, but that's what we have for the equations, and it actually works, and I'll show you how we're going to use it to solve our problem. Alright, so now let's simplify our set of equations just a little bit, and we get this set of equations over here, which is just a little bit more simple. Now, in order to solve our problem, we're going to start making assumptions. The first thing we will assume is that our light rays only travel horizontally, as in our problem. So now what this assumption translates to is, say that we have our nth light ray path. What it's going to be equal to is t minus k1 times x hat plus k2 times y hat. So since there's a t dependence in the x hats, that means that we're going to get a straight line in the x direction. There's no t in the y direction, so y is going to stay constant while x varies. That is a horizontal line. So the second assumption that we will make is that our surface is a parabola that opens to the left. And this means that we model our surface as s of u is equal to negative a u squared x hat plus u y hat, where a is the factor that determines like how wide our parabolic opening is, and x hat s simplifies to this over here, and r hat rev, that's just negative x hat because it's just a horizontal line. I forgot to mention that in the previous slide, but that's what it simplifies to. And finally, we will assume that a is equal to 1, which describes our parabola in the original problem. And we get this set of equations over here. And finally, let's solve the original problem. So we're going to model the first light ray as r1 of t is equal to t minus 50, where 50, that's just an arbitrary offset. We can set it to anything we want, but just to make things look good, we're going to set it equal to 50. And since it's going to be equal, since the light ray is a horizontal line at y is equal to 5, we have a 5 over here. And what we get is r reffle 1 of t. We get the equation that describes the reflected light ray as a response to this hitting the surface. And then we get to our second equation over here, r reffle 2, as a response of this light ray positioned at y is equal to negative 4 hitting the surface. So we have calculated these two equations, r reffle 1 of t and r reffle 2 of t, but these are parametrized by time. In order to figure out where they intersect, we're going to have to parametrize them by a path. So they're both going to have different p's. Let's just say that this one's going to be, instead of t p1, this one's going to be instead of t p2. Yeah, we'll do that. And if we do that, then we'll see that they intersect at negative 0.25 as the x coordinates. So the intersection point, the position vector that describes the intersection point, is negative 0.25 x hat plus 0 y hat. So here's a diagram to illustrate our solution. So our first solution, which was the reflected path in response to the light ray at y is equal to 5 hitting the surface, is this line over here. And the other one in response to y is equal to negative 4 hitting the surface is this line over here. And as you can see, they intersect right over here. And if we zoom in, we'll see that they do in fact intersect at x is equal to negative 0.25 and y is equal to 0. That point right there. Alright, thank you for watching and stay curious.